Thanks for the intro, Omar. So as Omar said, I'm Sumanth. My role here at Facebook is as director for a team called Traffic. The traffic infrastructure team at Facebook is responsible for building and operating the systems for our CDN, among other things. Unfortunately, the people that actually did this work were not able to be here. They went on vacation, but I'm happy to take the credit. So with that, let's start with just what a classic CDN looks like. Here we have all the content is stored in the backend on some kind of blob store for all our static content, images and videos and such. And we have a user that's fetching that over the internet, directly hitting the data center. And this could be up to 500 milliseconds of latency before you can get this content. So what that means is that we have to be able to do better than this. And one way we do that is to add an origin cache first, right next to the blob store in the data center. What this can help you do is two things. One is it protects the blob store from all the load that can potentially hit it directly from the internet. And the second is that the origin cache for anything that's actually cached in it is going to be much faster than the time it takes to retrieve it from a storage system like a blob store. So right there, that's going to cut down the latency substantially. The next thing is to move this cache as close to the user as possible, and we do that by building a network of POPs around the world. You heard a little bit about that from other speakers here today. And the edge cache gives you another big step in terms of reducing the latency that the viewer experiences. So we can cut that down in this example from 500 milliseconds to 75 milliseconds for the content that you can manage to cache here. And that's a huge, huge reduction in latency and a huge improvement in performance. So that's basic CDN stuff. Oh, one more thing to mention here is that with the edge cache, you can generally have a backbone that you build yourself, and so you have kind of a fast path to that rather than going through the public internet and competing with all the other traffic. Now, so live video. Live video is a product that was widely rolled out to the public by Facebook sometimes early 2016. And this is, it's been since extremely popular. Lots of really engaging content, lots of great use cases that have gone into that. I'm not going to go into the product itself, but the infrastructure behind it, there's basically two things here, right? There is the upload, when the broadcaster decides to broadcast the video, and that happens over RTMP, and that stream of video comes to our data center. And then there's the download, and that happens over HTTP2 today using the MPEG- playback format. When the RTMP stream comes into the data center, it's ingested by the live transcoder service. And the live transcoder service produces two artifacts. One is a manifest, which consists of a set of URLs of individual video segments that are in that stream. And the next one are the segments themselves. Now, the video manifest is actually regenerated as more and more video comes in, and the URLs roll through that. Okay. Now, here's a timing diagram of how this happens in a classic CDN. The first step is the client requesting the manifest file from the origin, and that request makes its way through the caches, through the various caches, hits a dynamic endpoint, which gives it the generated manifest file, and that goes back to the client. When it gets to the client parses it, picks out an individual segment, URLs for each of the individual segment videos, and sends a request for each of them, and that gets all the way back to the data center again, and the responses consist of the individual video segments. So this is a sequentialized set of things, as you can see from the diagram here. Now, in a proactive CDN case, the manifest request, when it hits the Webby, because, like for example, in the Facebook case, we actually control the client and the server, and we know when the video is coming in. So when the dynamic endpoint gets the manifest request, it knows a few things. It knows that this video is currently playing, that it is that this particular user is interested in it, and so we can use that to tip off another service that we call the priming service, the content priming service. And the content priming service gets to uses that hint to prefetch all of these individual video segments that it knows that the client is going to need and start sending them to the closest edge cache, right? And if we are successful, we can do this before the manifest file response actually gets to the cache, gets to the client. That way, after the client has parsed the file and starts sending out requests, by the time those requests get to the edge cache, the responses and the video segments are already there. This way, we can minimize the amount of time. Now, let's drill a little bit more into the infrastructure behind making this happen. So the priming service gets notified by the live transcoder service that new video segments have arrived, and it then pushes that to the right pop cache from which the viewer can then fetch it. However, you can't push this to every single cache out there, or you can't do this for every single video that's currently playing or that might potentially be watched. So you actually need a way to tell just which particular pop caches should have this, right? So we needed to then build a subscription map, and the pop caches, when they actually get requests for a given video, they subscribe themselves with the subscription map service and tell it that, hey, I have a user that's watching this video right now, so send me the future updated live video segments. And the priming service then consults the subscription map as new video segments come in, and it starts sending the video segments to the right pop caches. So by doing this, we were able to have a pretty significant reduction in latency. So we saw about a 60% reduction in latency. In addition to that pretty substantial reduction, there's another thing to notice here. If you look at the latency graph here, you notice that it has way less jitter than the other case. And this is important for latency in another way, because every video player has to buffer some amount of video ahead of time so that when there are little network blips and jitter like this, you don't get the spinner wheel, right? So when there is higher jitter, it means that you have to take the conservative approach and buffer more. But if the jitter is less, that means it's a little bit more predictable for the video player, and so it can actually buffer less. And so that's another latency gain that you get because of this. Similarly, on the hit rate, we get a corresponding 9% increase in hit rate as well. And this is an absolute number. That is, again, obviously a result of the priming. So the takeaways here for live videos are that to achieve minimal latency, the live video is particularly sensitive to latency because we find that live video is much more engaging to people if it is as real time as possible. Because when it is more real time, when the latency between the broadcast and the reception is reduced, it leads to, for the broadcaster, they can hear back from their viewers as pretty close to the time they actually, as things happen. That actually encourages them to do more videos to essentially have a much better experience. And similarly for the viewers as well, it is a much more engaging experience to be able to interact with the broadcaster as close to the real time as possible. Now the other thing to think about here are that we heard about zero RTT from Sumanth earlier today. Actually, establishing a connection, it is a big tax. Because all of these connections are also encrypted as well. It's a pretty big tax. And so it's pretty important to keep persistent HTTP2 connections open. Otherwise, you may not quite win that race to get the segment into the cache before the user's request comes along. This is also why we're working on things like zero RTT and so on. The subscription model is the third piece. You have to know which pops to push in order to avoid over-pushing or, on the flip side, under-pushing because you don't know which ones to push to. So those are the three things. Now, since this worked pretty well for live video, we thought about what else we can do with it, and it turns out we can actually apply the same idea to video on demand and images and other kinds of content as well. And similarly, just like the different types of content, we can extend this to caches closer and closer to the user as well. So we can do the same thing to push these images and video into caches deep in a service provider's network, as well as even directly to the client themselves using ideas like HTTP2 push. These are all things that we're exploring as well. Now let's take a little deeper look into what it takes to apply the same thing to images and video on demand. So in this slide here, on the right, you see the Facebook feed. The Facebook feed consists of hundreds of feed units with hundreds of little individual static items, like images, like video on demand, et cetera, that could be accessed by the user, but not all of them are going to be, right? So how do you decide what to push and when to push and where to push it? To do this successfully, we actually need a couple of new services. One is an ML filter, a machine learning filter, that is trained to be able to predict just which of these images and which of these videos that the user is going to play. And the other is a way to keep track of the cache state. So we actually need to be able to tell just which of these items are already in the cache and whether they have expired or not. So we do that with the service that we call with the service that holds the cache state. In order to do this in a compact fashion, as you can imagine, we have millions to billions of items in our caches worldwide. We use a sliding Bloom filter data structure, which is able to represent this in a pretty efficient way, in a tractable way for the scale that we're operating in. And with that, what we're able to do is that by the time the dynamic endpoint sends the feed response consisting of all of these embedded static objects in it, it also tells the priming service about this. At which point, the priming service then consults the ML filter to figure out which of these artifacts are likely to be clicked on by the user, and looks up the cache state to decide on whether or not it's in the particular pop cache that the user is hitting, and is able to find it and push it to that pop cache. And it has to do all of this before the requests for those items come into the pop cache, right? And so in this example, it takes about 200 milliseconds between the time the response starts its journey back to the client to when the client starts to sends a request and hits the pop cache. So in order to make this work, you have to win that race, and within that 200 milliseconds, you've got to select of all the URLs, all the objects that the client could be looking at, which ones they are going to look at, notify the priming server and give it a list of these things, fetch those images and transcode them, and push them into the cache. So you've got to do all of these things in time to be able to win this race and successfully deliver the content, so that the client can actually look at this in the minimal possible time, which is about half an RTT. So here's a little bit of data on how this filter works. The machine learning filter details are a little bit out of scope for this talk, perhaps another one in the future. But essentially, we have about a 95%. We have about 90% of the decisions that we make and send the content to the edge actually win the race to the edge. And the cache rate, we're able to get to about 85% with this approach. And what that means is that compared to the non-push case, we can actually cut down, in this example, from 375 milliseconds to about 120 milliseconds because of the increased cache hit rate and accuracy. So that's about a 15% improvement in the hit rate. But to actually make this work successfully, the key is to get your ML model to be accurate. What we found is that in addition to training this, it has to be kept current as well. With every day, we train this model every day, because without it, it tends to drift away and the accuracy tends to drop. But if you get this right, you can actually improve the cache hit rate substantially. And the other thing to watch out for here is the backbone usage. So while this works, it also puts an additional burden on your backbone. Now you're actually pushing content in anticipation of it being accessed by the user. But that may or may not happen. But for sure, you're going to hit a backbone usage, a backbone hit. And at peak times, some of your backbone might be congested. So if you try to push even more content on top of that, you're going to congest the backbone and make things worse than you started from. So you actually need to manage this pretty well. So what we ended up doing is to build a feedback service that actually monitors backbone to each of the POPs, sends a signal back to the priming server, and so that we can actually decide on a real-time basis whether the backbone is congested or not, whether it is worth pushing any piece of content or not. So with that, that's about the end of the talk. Happy to take questions.
Any questions? Right over there to the left.
Hi. A couple of quick questions.
Sure.
Is the manifest file itself not cacheable, or you seem to show that the manifest, every time you go to the web server and bring it, it's not cacheable at the edge?
So the manifest file is cacheable. However, it keeps changing, because as new video segments come in, the content of the manifest file will change. And so you have to keep refetching it to get the new set of URLs and the new set of segments.
Hi. It seems like most of the systems that go beyond basic caching are on the origin side and not the edge caches themselves. Does that imply that the cache servers themselves are running like something like Varnish or open source, or is it all a single in-house built system?
So all of our caches are in-house, built from scratch systems. It's not entirely true that the edge caches, the POP caches, do not have more sophisticated stuff in there. They do actually have some additional services as well. So for example, as I mentioned here, the subscription service, for example, has to run in the edge. It needs to be able to tell the subscription, the service that keeps track of which POPs need to have which content in the data center, it needs to be able to tell it. So they are more sophisticated. I don't know if did that answer your question? Okay.
One right here in the middle.
Hey, thanks for that. How does that 85% cache hit ratio compare to your user-generated images and other static content?
So it actually varies quite a bit. It's a big range. So I don't want to give you an offhand answer there. It varies depending on a huge number of things about how recent this content is, which part of the world you are in, and how much caching is available at that point, and so on. So there isn't this was a particular study for this particular segment of content, meaning in the VOD and image case, that actually improved by about 15%. So in that experiment, that went from about 70 to 85%.
Hi. One other question. How fast are you able to withdraw the contents when you have this kind of geographical distribution.
Meaning how fast can we invalidate the content?
Invalidate or withdraw. I mean, some be acceptable, it needs to be removed. How fast are you able to
okay.
withdraw those?
This is more of a cache purge. This is an interesting question. There, the answer also, it depends, is the answer. There are other ways of preventing access to the content than just by removing it from the cache. So one way is to not give out the URL. So a lot of our URLs have time limits on them. So once that time expires, you cannot use that URL anymore. We do have, of course, ways to purge a cache, but that also, that actually, it tends to vary as well because there is a queue of requests that goes out. Usually we can do it in a matter of minutes, but sometimes, there are outliers as well. But there are multiple ways of preventing that. So one is the actual removing it of the content from the cache itself, but we can also use the expiration time. We can also use what we call look-aside authentication. So you can also prevent access to a piece of content by failing an authentication for a given URL. So there's multiple ways we can do this, and it really the answer is it varies and it depends. Any other questions?
Any other questions? All right. Well, then thanks a bunch, Sumanth.
All right. Thank you.
Yeah.